First time using this, but path compression is faster. All right. Union find has many applications. Kruskal's algorithm we'll learn later on after the midterm. But one thing we can do is count the number of components in the graph. And that is what Lab 4 is. So if everyone has their computers out, let's do the Lab 4 coding assignment. Right. So this is kind of everything put together. We'll come back to this later. So if you go to Canvas, here, and go to the Lab 4 starter files folder, there should be 5 files in here. We have the starter file, which is called connected components.cpp. We have the make file, as well as 3 test cases that we can use. All right, so I'll give you time to download that. Let me know if you're done. These files, yeah. Make sure you put the files in the same directory. That way we can use a makefile on them and submit it. Okay. So I'm going to go over the specs very quickly. So in this case, we'll be given an input file that represents a bunch of vertices in the graph, right? So this is kind of an image of what it would look like visually. But you're actually not given that. You're given a test file with numbers instead. So the file comes in the following format, right? Basically, we have number of vertices in the graph. So in this case, we have 4. Number of edges. In this case, 2. And we have the edges here. So in this case, 0 is connected to 1, and 0 is connected to 2. And notice that 3 is not in here. But since it was specified that there are 4 vertices, then we have 0, 1, 2, and 3. So even though 3 is not explicitly listed here as an element with an edge, you can just treat it as an element that has no connections, so that's its own component. Otherwise, here we connected 0 with 1 and 0 with 2. So this forms one component. The 3 forms a separate component. Your program, if given this file, would return the number 2. So does everyone have the file downloaded? We're good. So let's start off. So we have some starter files here. Basically, we have a graph object, which stores number of vertices and number of edges. We also have find and union, and these are 2 functions we'll be using. We also have this function we'll be using to count the number of components after we've implemented find and union, and we'll get to that after we do the other 2. So union find. Here we want to initialize any member variables that we want to make our job easier. So recall what we talked about a few minutes ago in the slides. What should we have here when we construct this graph, right? What's something we need? I want to know the representative of each vertex in this graph. How do we keep track of that? Does anyone have any ideas? Well, recall, I'll pull this up again, right? called the slides. Like, what are these? Like, what's this? Well, I mean, is this even like part of the array here? This is just the index. So what do we actually need?
Just a 1D.
Just a vector, right? Or 1D array, right? That's all we need. And how many, what's the size of this vector? Number of vertices we have, right? So what do we need here, right? What should we initialize here? A vector, right? Call this representatives. And what should their size be again? It should be what? Vertices, right? In this case, is this number here. Does everyone follow those two lines that I just added? Okay, so that's not all, right? So we initialize our vector, and we resize the number of elements that we have, the vertices we have. But, I mean, they shouldn't all default initialize to 0. That's not what we want, right? So in this case, what do we want, right? When we start off with all these elements not connected, what should their representatives be? Themselves, right? So essentially, not only do we want a vector of size v, or a number of vertices we have, we also want to make sure that the element index 0 has a value of 0. The element index 5 has a value of 5. The element index 253 has a value of 253. So how do we do that? Fun fact, does anyone recall a special function that was covered in class that allows you to fill a vector using its own indices? Iota. Right? So you don't have to do this. Technically, we can just, for loop through the whole thing and assign each index of the vector with its own index value. But as we recall, I include this for you. Include numeric, which includes iota, which means you can use iota instead to just fill up the entire vector itself. That begin. So the beginning of the vector to the end of the vector, you're going to start with 0, and it's going to fill up 0, 1, 2, 3, 4, so on, until it reaches the end of the vector. Actually, since we have namespace, well, we don't, so I guess we just have to use this. All right. Well, let's move on to find. So, how did we talk about find previously? How will we implement find? Right? I pass in some vertex, and I want you to find the ultimate representative. How would you do that? Right.
If it is, you return. Otherwise, you check that representative.
Correct. Right? So you would continuously check the representative of V until you reach the ultimate representative. So if you recall from our slides here, we move up the tree, essentially, right? We call find on this person. We check who this person's representative is. And we check that person's representative. We move all the way up until we find that ultimate representative, or the element where the index is its representative, or its own representative. So how do we do this in code? Does anyone have an idea? Feel free to talk about it. with people around you. But how would we actually implement find? So we talked about how we would do it. How can we actually turn that into code? Yes?
Shouldn't reps be on the variable instead of variable dot graph?
Where is it? Oh yeah, that should be up here. Never mind. Yeah, put in the wrong place. There you go. There. Right, so what do we have to know? What's the first thing we should check for and find? We check if its representative is itself, right? And if it's not, we essentially keep on checking up the tree, right? So we can put this in a while loop, and we can say, okay, we're going to check the representative of v, right? And we're going to see whether or not it equals v itself. If it is, then its representative itself, then we can return it. Otherwise, if it's not, we'll have to do some searching, right? What should we put in here? Yeah, v is equal to reps v. Does everyone see how this works? What about union? How do we do union, right? What did we just mention previously? How do we join two groups together? I have two vertices that I pass in, A and B. What's the first thing I do? Yes?
Check to make sure they're not already in a union.
Yes, right. You want to check if they're in the same set, right? And how do we do that? What's a function that allows us to do that? Find, right? So just say, I want to find the representative of A. I want to find the ultimate representative of B. And then what I do, I check if they're equal, right? If they're equal, I don't have to do anything. They're part of the same union already. But if they're not, so if A's representative does not equals B representative, then we'll set one representative to have the other's representative. So in this case, let's just use B, right? So we'll assign reps of B. We'll assign B's representative to be A's representative. Does everyone follow that? Okay. So we're done with these two. We did find and union, correct? Now let's actually count the number of components. So who has ideas on how we want to do that? Right. So let's have an example file, right? Actually, I'm going to use the example here in the spec. Right here, correct? Actually, I'll use this one. So what's the first thing we read in? Well, we read in these two. I think that's covered for you already. You don't have to deal with this yourself. That's the first two CNs, right? And then we initialize the graph with these two numbers. So the next element you would be reading in would be the 7 here, right? And then you'll read in the 3. So how should you, I guess, go through this file and connect the 2 points together, right? I read in 7, I read in 3, and I want to join them together, right? How should I do it? Well, I have to do it for all the edges, correct? Right? So let's go through all the edges, right? Yeah. And I'll just initialize x and y here. I'm going to read in x and read in y, right? So this is kind of like a 7 and the 3 we had in the file. And we're going to do that the number of edges times. And we want to join x and y together in a union, right? So we have this function that we just wrote that allows us to do this. And we do checking for whether or not a and b have the same representative in this function. So we can just say, hey, let's just union x and y together. What happens at the end of this for loop, right? So we did our loop through the entire file. We looked at e edges, and for each of these edges, we read in 2 numbers and union them together. What happens after the end of the end of the for loop, right? What is the state of our reps vector at the end of this for loop? What does it look like, right? So let's look at this case here. What would the vector look like after the file has been read in completely?
0, 1, and 2 all have 0 for the representative.
Correct, right? You have a vector where 0, 1, and 2, this is the index. Right, so it's an index. This is not actually the vector itself. This is our vector that we have here. Right. 0's representative would be itself, but 1's and 2's representative would also be 0, since we combine the 2 and union them together in these 2 lines here. What about 3? What's 3's representative? It's 3 itself, right? That hasn't changed, because 3 wasn't actually unioned together to any other vertex in the graph, so its ultimate representative would be its original value, which we initialized to 3. So how can we count the number of components in the graph? Yes? Yes, right? The number of elements in here that have itself as its representative is the number of components, right? So if you remember from the example when we talked about the leaders of a country, if we're given, a list of people as well as, their leaders, the number of leaders that exist where their leader is their self must be the number of countries that there must be, right? So this is very similar. If we have these elements here in the vector, we essentially count up the number of elements that have themselves as their own representative, and that is the number of components that we have. So I'll give you a few seconds to type that up. I'll come back and type it up in a few minutes, like a minute or so. So I'll come back at like roughly 3:28. So complete this function, and we can come back together in a few minutes. Are we all done? Okay. So, as I mentioned before, right, we would go through our reps vector at the end of this for loop and check how many elements have themselves as their ultimate representative. And we can do that by, we can set some count value equal to 0. We're just going to for loop through all the vertices. And essentially what we're going to do is we're going to check, right? If reps itself is equal to the index, that means it's representative of itself, and then we can increment the count. Right? And then since we want to return the number of connected components they are, we can just return count. Does everyone follow what we did here? We reddened each of the edges, union together, and then we went through the reps vector and counted the number of instances where the index of that vector is equal to the value of that vector itself. And then we return the number of instances we found. But there are also different ways to do this. This is not the only way to do this, and doing the count from 0 and then looking through the entire vector. There may be faster ways to do it. That's up to you to find out on your own. But this is just a simple solution where we just go through the vector and count the number of times we have the elements represent themselves. Okay, I think we're done. Let's compile this and see how it works, right? So essentially, I'm in this file here. We have 3 files here called test1, test2, test3. They should have the solutions of 3, 7, and 6. And so we go through and say, hey, let's run this, right? Let's run make. It compiles. That's great. We got this executable file here called connected, right? And let's run connected on the test case, right? That we have. Oops, how to drag this out. There you go. All right. We'll run this, and we should get 3. And we do. And so it works, right? Let's run the second one. It should have 7. 7, sweet. Last one should have 6. Great, our program works. Let's submit it. All right. Let's submit it, get 10 points. We're done, right? This is so much easier than lab 3, right? Let's make full submit. We make a tarball here. And let's submit to the audit grader and call it a day, right? It's been a long week. Exams are coming up. Let's just submit this. Oh, there's 4 people in the queue. All right. Let's do this. Oh, gosh, come on. 211, 281, lab 4 demo. Here it is. Let's submit this file. Let's have some fun. I'm at the end of the queue. Oh, you guys all beat me. That's nice to know. But I'm here at the very bottom. I'm queued. Just a fun fact, this can only run 6 at a time, the auto grader, which means if you're number 7, you have to wait until everyone else is finished, right? So I'm waiting here, and wow, everyone else is taking a long time. Right? This shouldn't be happening. Why is everyone taking it, you guys are still 15 out of 18? I just started. Okay, that's great. That's not good. Well, I mean, think about the amount of time it took to get 3, 7, and 6 as the answers, right? But we have here, I'm currently running, I'm still stuck at 10 out of 18. It's been a whole minute. I submitted at 3:31, and it's now 3:32. That's not good. Am I still stuck at 10? Huh. That's interesting. So what went wrong? Right, so obviously, it's not that easy, right? We're not going to get 100 points that easily in just a few minutes. So what went wrong here? Right? I'm still stuck at 11 out of 18. And it's taking a long time. This person here who submitted first is still at 10. And we're all here waiting in the queue because something wrong has happened. Right? So I'll give you a few minutes to think about what exactly could have happened. Right? This shouldn't be happening. But we had a correct solution. The solution we had was correct. I'm going to say that. The solution that we just wrote is a correct implementation and would get the correct answer to all the test cases. But why are we all sitting here in the queue? Right? Someone on project 2 just showed up. Right? Why are we all sitting here in the queue? Right? Give you a few minutes, think about it, and try to make a fix that would solve this problem and have your code run correctly on here.
Okay, so it's a problem with the code. All right.
The problem is with the code. The code is correct, but it's not efficient. All right, so I'll give you a few minutes to try to implement a solution. And I'll wait here until we're done. Right, so. The first one hasn't finished yet. This person submitted at 3:27. I don't know if they're in the same class as us, but that's a long time. I'm still here, right? We're still 16 out of 18. It's been 3 minutes. Now it's been like 4, because it's going to turn 3:35 soon. So, and we're still, one more though, 17 out of 18. We're almost done. Almost done. It's been 4 minutes. We're almost done. This person's almost going to be done with entire project 2 before we get done with this. That's how slow this is, all right? Oh, sweet. Our score's back. Let's see what we got. See this. Oh, that's nice. We passed the first 3, which is expected. Oh, we passed more. That's nice. Oh, wait. What happened here? Wow, 70, what? 72 times? What happened here? We went 72 times over the speed. We're supposed to do this in 0.4 seconds, and we did it in more than 35, which means our program got killed by the autograder because we were too slow. Oh, look, what? 4.64 out of 10. That's terrible. What happened? Look at all these TLEs here. Wow, 27 seconds. How do we get these times? Now, this is me testing it beforehand. Right, we want those times. We don't want this. By the way, the answer is not breadth first, depth first search, as you mentioned before. That one's actually this one. That was me testing with BFS, DFS. You don't have to worry about that. But how do we fix it using union find? Right? Union find is faster. But this is so slow. Right? Who has an idea? Yes?
Because when we're trying to set like two units together, we didn't set the other representative from the other.
Wait, so you said that we're unioning A and B, right? We set B's ultimate representative to A's.
Representative of B. Like,
Right.
But we didn't do past compression on the other.
Yes, right? We only set B's ultimate representative to A, right? Well, let's word it this way, right? Every time we call find on an element, we don't path compress, meaning that we're going to do a whole bunch of work that we don't need to do, right? So if we recall from what we talked about in the slides here, if I can pull this up, what do we have beforehand? Let's look at this, right? This is path compression, right? So not only do we return the ultimate representative when we call find, we also set all the elements along the way so that they have the representative, their ultimate representative as well. So we don't have to do additional work every time we call find. So let's fix that, right? Oh, sure. Let's fix this. So this is correct, but it's inefficient, and we don't want that, right? So let's fix this to make it path compression. So how do we do that? Well, we say, let's just copy the code from the slides, right? If the representative is itself, right? If we have its representative is itself, then what do? I return v, right? Otherwise, I'm going to assign all the elements along my path to the ultimate representative to that ultimate representative, right? So I'm just going to set each of the representatives along the way to the ultimate representative of along the path that we're going. Does everyone follow that? Right? This is from the slides itself. And then we can return whatever value is at the end. Let's compile this. Make sure it still works. Right? It should be 3, 7, and 6. 3, 7, 6. We're all good. Let's make a turbo. Let's see how fast this runs, right? So this one we got 4.6 out of 10, which is a very terrible score, right? But we can now use path compression. Let's take this file that we just recently created, and let's see how fast this runs, right? So I'm going to click submit now. We're going to check the runtime, right? So we're here. Oh, look, we're at 11 already, right? It's a lot faster. You can see the progress going. It's going pretty fast, right? We're no longer sitting on the queue with 20 other people who are also trying to run lab 4 without path compression. So the last two cases are a bit slow. That's because they're very big. And that's not because the program is inefficient. Going up, that's nice. Let's see. Boom. All passed within the runtime constraints. Right? It might be a bit slow right now just because there's so many other people trying to run at the same time. But the times look a lot better. Right? So in this case, this test case here, or without path compression, we went over. Now we finished it in 0.319 seconds. Right? That's very, very nice. Similarly with this one, we have 27 seconds. We dropped it down to 1. That's a 26-second difference just by using path compression. So union find, use path compression, right? That is the way to go. So that's it. If you submitted and you got full points, you receive full points for this week's labs. You just only have to do 4 multiple choice questions. And hopefully that'll give you more time to do the project and study for the midterm. But if you want a challenge, you can always find different ways to optimize your program to make it run faster. Right? So in this case, this is 12 seconds here. You see that? It might be a bit slow just because there are many people in the queue. You can drop it down lower. Similarly with the other times, you can drop it down lower as well. So the solution we did was a very simple solution that works. But if you want a challenge and you want to devise new ways to make this faster, feel free to do so. Although it's completely optional, if you submit it today and got all the points, you will get full points for this week's lab coding portion. So that's it for the demo. There's also a few extra slides you should look over for project 2 on functors, pairs, and other stuff. But let's do the handwritten problem, and that should be the end of today's lab session. So get out a piece of paper, and here's the problem that we have. We want to find the minimum cost of connecting 2 ropes, given that the cost of connecting them are the sums of their lengths. Just as a hint, we talked about priority queues today. So the solution to this problem uses priority queues.